possibly made it worse than magic somehow.
Fair enough. But I try not to be harmful. Anyway, that's a different discussion. All right, team, so let's get to it. By the way, you'll sometimes see formulae as the plural of formula. That is sort of the traditional accepted plural form. More and more often now you'll just see formulas, but let it never be said that I miss a chance to be pretentious. So here we go. We're going to talk today about empirical formulae and molecular formulae. Yesterday we learned that if you do an experiment, you can find the mole ratio of each element in a compound. But there is something you have to watch out for in covalent compounds, because we said ionic compounds are what? They're big dumb rocks, which is to say there's only one way you can put them together, because they just form these big crystal structures. They just keep growing, right? So in fact, we say there's no such thing as a discrete sodium chloride molecule. Sodium chloride is NaCl, but then as it gets bigger, it's Na2Cl2, and then Na3Cl3, Na4Cl4, and really with an ionic compound, that ratio is just that. It's the ratio as that crystal grows. Molecular compounds are different. They're individual molecules where you draw those discrete bonds. So even when you get ice, which is crystallized water, it is not a network of covalent bonds that just keeps growing. It is still individual water molecules that are two H's stuck to one O that are interacting with each other. In covalent compounds, you get these discrete individual molecules of covalent bonds. And what that means is that C5H10 is not the same thing as C8H16, even though if you notice what is true about both of these. There's half as many carbons as there are hydrogens. In fact, we could write a whole family of things that have this same ratio. CH2 would be the same thing as C2H4, which would be the same thing as C3H6 if they were ionic, but they're not the same thing in covalent compounds. These are all different molecules with very different properties. In grade 12 chemistry, which I hope you'll all take, we'll learn a little bit about how we can anticipate the physical properties of compounds based on their formula like this, but these are all very different from one another. In fact, CH2 doesn't exist, but that doesn't matter. We'll get to that later. But what they all have is they have the same mole ratio. And the mole ratio they have is 1 carbon to 2 hydrogens, right? Which we could actually just write as a fraction like that. And as such, we say that these have an empirical formula of CH2. In other words, if you did the experiment we did yesterday to find the formula of any one of these, what you would end up with is an empirical formula of CH2. And again, for an ionic compound, your work would be done when you had found that its empirical formula was CH2. But with a covalent compound, your work isn't done. Because with a covalent compound, if you find out that the empirical formula is CH2, you still don't know if you're talking about C2H4, C3H6, C5H10, C8H16, or you'll discover that carbon chains can be incredibly long. This could be C100H200. Do you know what I mean? We don't yet know from the empirical formula what the actual compound is, if it is molecular. In other words, if it is what kind of bonding? That's right. When we see the word molecular, that means covalent compounds. So, what do we do with that? How do we work it out? Well, I'm glad you asked. What we need is a bit more information. So, the first thing we need to do is indeed to find the empirical formula of the thing. And we can do that. So, let's just make sure we know how to do that. A sample of hydrogen peroxide is decomposed. It is found to contain 5.3 grams of hydrogen and 85.4 grams of oxygen. Let's find the empirical formula. All right. And this is review from yesterday, but shall we do it together, or do you want to take a crack at this? Let's do it together. So we've got two things here. We've got 5.3 grams of hydrogen, and we've got 85.4 grams of oxygen, right? Okay. All we need to do is not talk about grams. We need to talk about moles. So let's do that. How do I do that here? Obviously, I multiply by a fraction. That's going to become like our orthodoxy. That's just what we do. What don't I want to talk about? Where do I put that? The bottom. What do I want to talk about? Yeah. And again, we don't have to make this H2. We don't have to make it diatomic because it's not by itself. It's in a compound. We know that, right? How many grams are in a mole of hydrogen? Well, we're only in 2 sig fig land. Well, 3 sig fig land here, so we'll do 1.01. That should be fine. And so this should obviously be 5.3, right? When you do that division, we're going to get 5.3 moles. All right. And this one, a little less easy math, but still pretty easy math. I want to cancel grams of oxygen. I want moles of oxygen instead. And what's the ratio here? 1 mole of oxygen weighs how many grams? 16.0. And that's going to give us what? Okay, so also 5.3 moles. In this case, 5.34. And now what would we do to get the mole ratio? I mean, you can probably already see it. Hey, guys, what's the mole ratio?
1 to 1.
1 to 1. They're the same. But, so we know how to do it, what's the process here? We divide both numbers by the lowest one. So we're going to divide them both by 5.3. That's going to immediately put us in 2 sig fig land for both of them, right? And we're going to get 1.0 moles of hydrogen and 1.0 moles of oxygen. And that means that the empirical formula of hydrogen peroxide is H1O1, or we would just write it as HO. Now, is that the actual formula for hydrogen peroxide? No, we know the formula for hydrogen peroxide. Does anyone remember it? You may not. We've interacted with it once in a while. Well, doesn't actually matter. I'm glad you don't know, because what we can say from this now is, what would be the possible molecular formulas? So the possible molecular formulae would be anything with that ratio. So what would be with that ratio? Well, it could be HO. That could actually be the formula. But this could just as easily be H2O2. Does that make sense? That also has a 1-to-1 mole ratio. It could also be H3O3. It could be H4O4. Obviously, this could stretch out all the way to, could it be potentially H100O100? So on and so forth. You could just keep going. Does that make sense? Any of these could be correct. Without other evidence. Now, we're going to learn later on how we get that other piece of evidence, how we know which one it is. Does that make sense? But for now, we'll just say that this is the empirical formula, which means that one of these has to be the molecular formula. And then we could figure out some other ways to figure out which one is which. And we'll come back to the other ways to figure out which one is which on the next page. Any questions about that? That's okay? All right. Next, we discover that if you take a compound of sulfur and oxygen, so some compound of sulfur and oxygen, you don't have to write this, which is S question mark, O question mark. I do see a kid. I'll be with you in a minute. Do you want to check to see if it's something you can answer?
I think it's the same question she asked me, but I couldn't answer it.
That's fine. Just encourage her to skip it for now and come back.
Okay.
All right. So we want to look at that. Now here, they didn't actually give us grams. What did they give us? Percentages by weight. Now listen, if they give you percentages by weight, don't let that stress you out. they haven't told you a specific size. You could have any amount of this stuff in front of you. You could pretend you have 11.6 grams, and then half that mass would be sulfur, half that mass would be oxygen. Or you could pretend you have 12.2 grams, in which case half of that would be sulfur and half would be oxygen. Hey, what would be a really easy number to imagine that you have in front of you? 100. In which case, 50.0 grams of that would be sulfur, and 50.0 grams of that would be oxygen. So you'll note here, if they give you a percent composition, just replace that percentage sign with grams and go from there. In other words, if they're saying 50% sulfur, 50% oxygen, say, great, I'm going to imagine I have 100.0 grams in front of me, which means I'm going to have 50.0 grams of sulfur and 50.0 grams of oxygen. Does that make sense? I want you guys to try this one. Figure out the empirical formula for me following the same thing, and I will give you that head start where we say you can assume you have 50.0 grams of sulfur and that you have 50.0 grams of oxygen. Go. You got this. Hooah.
Sulfur is spelled with an S. I don't know why there's a PH.
Okay, so I'm not stupid.
You're not stupid.
I was like, what? I was like, what?
That's crazy.
PDH. I was like, what the fuck is that? I was like, he's saying sulfur. I was like, what? What's the sulfur? Please don't look back. No, but they don't have this one.
Yeah, I would have to.
Did you divide it?
I'll divide it out. Or no, do I round it all up?
You don't. Yeah, you round it. Yeah.
Okay.
Yeah, so you don't round. You don't round it in the middle. You round it at the end. Still.
Because you get the real thing, you get like 3 hours to exam and it's, 4 hours worth of fun money. And you want to get one to do right. Got such an important skill. Some people know the way that. The difference between 80s and 60s. You got this. All right, can we take a look at this? How do I approach the 50 grams of sulfur? What do I do with it? Yep.
Do that analysis thing,
Mm-hmm.
and then put 1 mole at the top, and then 32.06 grams on the bottom.
Great. Of what? Moles of what? Grams of what?
Sulfur.
Yeah. And I know that seems silly, but the more you go in chemistry where you'll deal with lots of things, it really is helpful to make sure you're never just putting grams. You're always saying grams of what. Great. What do we get when we do that? Obviously, it's going to be 1.56. I was going to say 1.6, so there we go. 1.56, 1.56 what? Moles of sulfur, good. And obviously when we do this, we're going to divide this by, we're going to say 1 mole of oxygen is 16.00 grams of oxygen. And that's going to be on the order of like 3.1-ish, 3.12. Yeah.
So for like the oxygen part, when you did 1 mole over 16, is it like necessary to round to 16? Because like on my paper I wrote.
If you left it as 15.9994, we're going to get the exact same answer. Yeah. Since we're only working with 3 sig figs, I was happy to just put 4 sig figs for the mass here. And some of your some periodic tables will say 16.00. Some will say 16.0. Some will say 15.9994. If you go online, a periodic table might have 7 decimal places in the mass. It just depends. But that's a great question. The answer is, as long as you follow sig fig rules, even if you use a really low number here, it may lower your sig figs at the end, but you'll be correct. You'll be accurate even if you're not as precise as you could have been. Good question. What do we do from here? Yeah. Great, which in this case is dividing them both by what? 1.56. And when we do that, this one happens to work out just perfectly, right? Which is funny. Isn't it funny that when you see these, it feels like this is bound to be like not perfect, but by virtue of sulfur being twice as heavy as oxygen, you get nice data. So we end up with 1.00 and 2.00, right? So that is obviously, nice, easy data. There's no need to round. So what is the empirical formula of this sulfur oxygen compound? So the empirical formula is SO2. Now, what are the possible molecular formulae then? What could this thing be? Whoa, what the heck is that? Now I'm having a moment. Bless you. So now we would want to do some further test because, yeah, this could be S2O4. What else could it be? I guess it could be S3O6. Don't forget, it could be SO2, right? What else could it be? I don't know. Could it be S20O40? I don't think that's very likely, but it could be. I don't know, right? It could be an infinite number of things. Does that make sense? Now, practically speaking, it's not an infinite number of things, but in theory, could this be S1 million, O1 million? Yes. Is that very likely? No. But there we are. So we would have to do some kind of further analysis to determine which one. Yeah.
Sulfur is spelled with an F, correct?
It's spelt both ways. The British spell it with a PH. The Americans spell it with an F. We tend to go F, but sometimes the PH will sneak in. Yeah, it's confusing, but both are considered correct, actually. So further analysis needed to identify which is correct. Yeah.
With the pH, does it change the way like things like sulfide and stuff like that?
Yeah, so again, the Brits would spell it with a PH.
Okay.
And again, we tend to spell it with the F, but I'm bad for going back and forth. Well, I'm not bad. Like, I'm not like, I don't need to like be put in the corner. But
Dunce hat.
wow, you went to dunce cap real quick. Then Max reaches into his bag and pulls out a dunce cap and is like, have you been waiting for this moment, Max? Anyway, like I saw that star you drew, Orlando. Dunce cap. Bam. How's that feel? So far, it feels exactly like yesterday's lesson, right? So now, the next step is, if we want to know which of these is correct, the easiest thing that we could have available to us is if we knew how heavy one of these molecules was. Does that make sense? If we knew the weight of a molecule, we could test whether it was SO2, S2O4, S3O6, S20, 40, And there is something called a mass spectrometer. You don't have to know this. Old note there. That should say E-Stale. That's funny. I grabbed an old version of this by accident. I don't teach at South Lincoln High School anymore. Heck, South Lincoln High School doesn't exist anymore.
Wait, actually?
Yeah, it's closed. Now they all go to West Niagara. Wow. South was adorable. It was this tiny little school. It was like 300 kids, only it was like jam-packed. Like that was just how big it was designed to be. And it was just this like really adorable little high school out in the country. And the kids all called me sir. And they all drove trucks to school. And every once in a while they'd do a spirit day that was like camo day. And you know what that looked like? It looked like every other day. Because kids just wore camo every day. But they would still be like, this is what we're doing. And when it was moose season, sometimes there'd be a bunch of kids missing from your class. And you'd check the attendance. And when it gave a reason for their absence, it would say, moose season. And you'd be like, that's a highly specific attendance code. Anyway, South was cute. It was nice. But not where I teach anymore. Look at that. Anyway, and nor have I taught there for 9 years. So, I probably could have changed this note. I did change this note. This is an old one. Now, right? Just working my way. Never worked at West Park. Guess I could work at West Niagara. And do we have a North?
We probably do.
Is there a North something in the DSPN? I don't think so.
Maybe. Who knows?
No. So there we go. So half the compass roses as far as I'm going to get, I think. Okay, so listen, you don't need to know this, but a mass spectrometer is a clever little device. And it's a device where somebody figured out quite cleverly that with a little bit of physics, have you guys done centripetal motion yet? Like angular momentum, like revolving in a circle? Don't worry about it. You will in physics eventually. So here's the deal. What we basically found in this, if you take a sample of some compound, whatever it is, and you blast it with energy. We blast it with energy. Look at us, we're blasting it with energy. What you can get is you can get to ionize. Basically, you can get it to spit itself out in a stream of particles. All right? Stream of particles of that compound. And they'll just go in a straight line, right? If you put a little, you put a little grating here so that they can only go out in one place, then they'll just leave in a straight line. Does that make sense? Obviously, it'd normally go in all directions, but if you all you need to do is put like a nice heavy lead weight and lead wall there, just put a little hole in it, and now you'll get a stream of particles of that thing. They'll just shoot out. And eventually they'll lose energy and they'll just, either end up in the air if they're light enough or fall down to the ground as part of the dust around us if not. But you can shoot out a stream of particles. Does that kind of make sense? And then you could have some detector here that they hit. And you could have it just, be designed that when a particle hits it, you get a little signal. All right, who cares? Well, here's the clever part. If you then put a big electromagnet around it, like this, you can apply a force on it. And you can provide an electrical force. You could make this the positive side. Oh, that can't also be the positive side. That the negative side. And what will happen is that because these have been ionized, they will get pulled towards this side. Does that make sense? And so they will take a curved path until they hit the detector. Does that make sense? Now again, you don't have to know any of this. None of this matters. But just if you're curious, how does this thing work? And if you measure the radius of that curve, you can do some pretty simple physics, and you can figure out the mass of the particle. If you know the force of the electric field, you can figure out the mass of the particle by figuring out how much it curves. A heavy particle, a big heavy one, would curve less, right? It would still curve, but it takes more force to move something heavy than it does to move something light. So a lighter particle curves a lot. A heavier particle curves less. A really light particle, say hydrogen, would actually curve around and strike back this way, right? It will actually make its way around. It'll actually strike a detector here. So we can calculate the radius of the curve that it's taking, do a little bit of physics, not even actually that complicated of physics. We can figure out the mass of the particle. This is how, we've been doing this for a long time. This is how they figured out the mass of the individual atoms, right? So that's how scientists were able to figure out that hydrogen and helium, that helium is 4 times as heavy as hydrogen, because when they did this with hydrogen gas, it made a big curve, and the curve that you got from helium was 4 times less steep. Now again, do you have to know how to build a mass spectrometer for this course? No, but that's all one is. And if you had 10 grand, you could go buy a cheap one. If you had 100 grand, you could go buy a good one with a nice little flame ionization detector on the end, and you can pump into it whatever sample you want, and it will tell you how heavy it is. Does that make sense? And this is a standard piece of lab equipment in an analytical chemistry lab. All right, so this is a piece of equipment that is sophisticated, but we're not talking like nuclear reactors here. This is a thing that a lab can just buy. You put in an order in the mail, it comes in, you install it in the lab on the benchtop, and then you can run it. Does that make sense? And what it tells you is it tells you the molecular weight of a compound. So let's look at this. Now, you probably already know the formula of glucose. But I'm going to tell you that we've already done an experiment and we figured out that it has an empirical formula of that's so frustrating. SCH3U. So the empirical formula of glucose is SCH3U. What are the possible molecular formulae? It could be CH2O. It could be what else? C4H. What would the H be here? 8. And what would the O be? 4. It could be C3H6O3. It could be ... It could be C20H40O20, right? We have no idea. It could be any of these. Does that make sense? Okay. How do you figure out which one's which? Well, here's the other piece of the puzzle. The other thing they tell us. They put it in the mass spectrometer, and we know that a mole of this stuff weighs 180.16 grams. Does that make sense? Now, if we know that, here's what we do. Find the molecular weight of the empirical formula. So what would the molecular weight of CH2O be? Well, that would be the molecular weight of carbon plus 2 times whatever hydrogen weighs plus whatever oxygen weighs. And that's fairly trivial to do because carbon weighs 12.01 grams per mole, right? Yeah. No. The molar mass of the actual thing is given, right? So that molar mass could be now you could just test all these. You could just find the molar mass of CH2O and C4H8O, and you could just keep going until you find one that matches. But that could potentially take a long time, right? Because there's an infinite number of possibilities. So instead, we're going to find the molecular weight of the empirical formula. Yeah.
Molecular weight. Can you take the one it gives you and then divide it?
That's exactly what we're going to do. Yep, exactly right. Well done. See? Look at that. What a clever kid.
I want to go about my
Here I am complimenting your intelligence. You're like, oh God, I just hit myself. That's okay. We're going to ignore that. I'd give you a star, but I don't know how to draw one. So no, I'm really good. I'd give you a star, but it'd be more than you deserve, ? I don't know. Anyway, let's focus. So, carbon weighs 12.01. Hydrogen is 1.01, right? And oxygen is 16.00. And what do we get when we do that? How much? Great. And you might already look at that and be like, oh, I can see, first of all, I can see that CH2O isn't the real compound. The real compound is one of these bigger ones, right? Because 180.16 isn't 30.03. This one's pretty nice. If you know your times tables, you can probably eyeball how many times bigger the real thing is. Right? Because you probably know that what times 3 would be 18. Yeah. So 6 times 30 would be 180. But you don't have to know that. Because now here's what we do. Step 1 was find the molar mass of the empirical formula. And then 2 is find how many times bigger the real thing is. And the way we do that by the way, if this were a mass class, I would have just said find the ratio of the masses. If you find that more helpful, you could say that. Find the ratio of the masses. If you're a real math nerd. So what we could do is we could find the molar mass of the molecular formula divided by the molar mass of the empirical formula. And when we do that, we're going to put 180.16 over, 30.03? And that's going to work out to be what? It's going to be just shy of perfectly 6. 5.999. And because we're not worried about sig figs here, inherently we're always going to be rounding when we do these questions. I'm just going to say we get 6.0, right? Which means the actual compound is 6 times the empirical compound. Does that make sense? So then we can say, okay, well, it's SCH3U, but we're doing what with all those numbers? We're multiplying them all by 6, which gives us, so that's the empirical formula, and the molecular formula then would be C6H, 6 times 2 is 12, 1 times 6 is obviously 6. Now, you probably knew that that was the formula of glucose, right? Because we teach that in biology class. But if you didn't know that, we just figured it out. Yeah. Except the empirical formula by definition will be the lowest terms possible. Now they might match. So what you will find sometimes is that the molecular mass of the empirical formula is the molecular mass of the actual thing, in which case, for example, sulfur dioxide, you'd find that. So this example we did up here, the actual formula of this thing is SO2. It's sulfur dioxide. So when you did it here, you would find that the weight of the empirical formula and the weight of the molecular formula were the same. And that would tell you that you just multiply it by 1. In other words, the empirical formula is the molecular formula. Is that what you were asking? Did I answer it in a sufficient manner? Would you give me a star? Great. And do you know how to draw a star as well as I do? Okay. Interesting. Is this a skill everyone has?
Yes.
Except me? Am I the one person lacking this skill?
I spent 2 days sitting under a desk.
Quiet! That sounded derisive.
What?
That sounded insulting. That was petulant and dismissive.
What?
I have feelings too, Annie Novak. I'm a person. If you prick me, shall I not bleed? If you tickle me, shall I not laugh? If you poison me, shall I not die? And if you wrong me, shall I not revenge? And if I resemble you in the other things, shall I not in this also? Oh, it will go hard, Annie Novak, but I will better the instruction. Anyway, many a time and oft on the Rialto. Have you guys read The Merchant of Venice?
No.
No,
Have you not read The Merchant of Venice?
No.
Oh, it's very good.
my dad's gonna make me read it.
It's good. It's, it's racial sensitivities maybe aren't what we would want in 2025. But again, it was written 500 years ago. So, kind of can give it a pass on these things. But it's very good. Very good. Anyway. I'm going to go on my, what's that? The one where you rate the books you've read? Goodreads? Is that the one? I'm going to have a Goodreads account.
No.
I'm going to log into my Goodreads account and review The Merchant of Venice. Anyway.
There's reviews on the Bible.
Well, why not? It's a book. I don't know why that's unreasonable. Like, I actually took a really interesting course once in reading the Bible as literature, which I really enjoyed. I that was a class that was offered in my high school, and I thought it was a really, really good, really interesting course. I enjoyed it a lot. And it was especially an interesting perspective because I went to a religious high school, right? So, I mean, obviously the Bible was interpreted as a sacred religious text sort of on a daily basis, but it was very interesting to come from the perspective of just reading it as a text like any other, which is actually something I would recommend, whatever your religious persuasions, to read both your own religious sacred texts, but also those of other religions, even if you don't have a religion that you subscribe to read the religious texts of the major religions sort of as a piece of literature and as a way to understand people who hold those beliefs, I think is a really interesting, really valuable experience. But then also to read them in the context of like, this is also a book that was written down and that's interesting. It carries a lot of weight, right? The Bible is a really interesting thing because how many other books that you can date back, at least in its earliest chapters, 3,000 years do we regularly read? And the answer would probably be not a whole lot, right? Maybe the Odyssey, maybe like, a few of those sort of classical pieces, but not too many. And it's a weird thing too, especially when like in, Christian circles, if you're in the English speaking world, we don't have a lot of texts in English that date back 3,000 years because English didn't exist 3,000 years ago, right? Like you got to go back a few hundred years. You can do Chaucer, you can do Shakespeare. And before that, English isn't even recognizable to us. Whereas like people still study Attic Greek and Koine Greek, and there's people in like the Western world who can read this 3,000-year-old text in its original languages. That's interesting stuff. Anyway, that's not what we're talking about here. But so I'm going to log on to my Goodreads, and right after reviewing the Bible, I'm going to review The Merchant of Venice. Then I'm going to review this lesson. I'm going to say, got a little sidetracked. But, the core of it was pretty good. 3 stars. So, now I want you to try. But this one, you got to do it all the way through. This puts it all together. Because I've given you percent composition. Now we said don't panic when you see percent composition. When we see percent composition, we're going to assume that means what? We're going to assume that we had 100 grams and just go. So you're going to have to use that to get the empirical formula. Then I gave you the molar mass of the actual thing. Get on it, team. You can do this. All right? You got 25 minutes. You're not going to need that. You're going to have this done in 12 minutes. Get to it. Yes, sir.
So, question. It gives us like 194 grams. Would we divide it by...
Look at the previous... I'm not trying to be dismissive, but I want you to fight your way through this. Look at the previous questions and see what to do, okay? Definitely, if you can't figure it out, I'm here, but I really think you can figure it out. You got this. That's right. And again, if you want to, pretend you have 2.685 grams, but then you're going to do a bunch of needless calculations. The easy thing to do is assume you have 100 grams, and then those percentages just become masses. Yeah.
Yeah. No, I'm giving you random skittles.
I don't understand. This actually isn't too difficult. I'm not doing it, but if I get that on the calculator, do I just round to that?
Yeah, so this is where we have to make assumptions, right? So if you were to turn this into a fraction, you would have to multiply this by like 12 to make it, you know what I mean? So now you have to use your judgment and say, do I think the empirical formula is C48 H60 O12 N24, or do I think it's more likely that it's that rounds to 4, that rounds to 5, that's 1, that's 2? You got to use your judgment.
Okay.
And then my advice is always stick with the rounded version, do this step, and if this step works nicely, then you were definitely right. That works beautifully. Okay, do you know what I mean? But it is a judgment call. Okay. And it's why in the lab it can be very tricky, because these are still very nice numbers.
Mhm.
What happens if it's like 3.89 and
Yeah.
4.87? Then you're like, yeesh, I don't know.
Yeah.
Do you know what I mean?
Mhm.
So it is a judgment call.
Okay.
And learning, because if this was 3.81 and 4.83, I'd be like, no, that's too much rounding. And in the lab, I'd say we got to go back and try again
Yeah.
and see if we're consistently getting that. If we're consistently getting that, this is going to be a really big molecule,
Mhm.
right? Do you know what I mean? Like
Yeah.
that's too much rounding. This is an acceptable amount of rounding.
Okay.
To 2 sig figs, this is 4.0 and 5.0.
Yeah.
And I would say if you've got that to 2 sig figs, you're pretty confident.
Okay.
Does that make sense?
Yeah.
Cool.
All I have to do now is the
That's right.
multiplying the actual like
Yeah,
formula.
beautiful. Does that make sense?
Yeah.
Awesome.
Will we be taking this out or no?
Yeah, we're going to take it up in 2 minutes. I asked for a black coffee and I got a regular coffee this morning. That's nice. Yeah, it's nice. It's good. It's too sweet. It's good. It's fine. It's too sweet.
Oh, I'm excited for Film Club tonight.
Me too, except I can't be there, which is the story of my life this year. The play. The play. This is my life.
It's a good movie tonight.
I know. What do you hate?
I hate that set.
I'm sorry.
But
Yes.
Are there any rules about like which element you hit first?
Yeah, as a rule of thumb, and nothing's perfect. As a rule of thumb, we work left to right on the periodic table, and then H is a wild card. H is crazy. It'll end up all over the place. It usually isn't put first unless you're talking about an acid. By convention, when we see an H in front, we assume that we're talking about an acid. So even though the left to right rule would normally put H in front, we'll usually put it after unless it's an acid. So we usually end up being put second. So generally speaking, move left to right, but there's a little bit of wiggle room, and you sort of develop a feel for it as you go.
Yeah, 'cause what is that?
And then sometimes, instead of we'll say C2H, sometimes we'll even write something like C2H5COOH. And you look at that and be like, why in God's name would you ever write that? But writing it this way lets me look really quickly and see some functionality of it. So the other way you could write this, of course, would be C3H6O2, right? And those are both acceptable ways to write it. So there is, in fact, a lot of kind of variability depending on what you're doing with it. But I would say as a rule, go left to right on the periodic table. Also, as a rule, don't put H out in front unless you're talking about an acid. And also don't put H on the end unless you're talking about an acid. Whatever. Just, yeah, you'll get a feel for it. And I'm not going to mark you wrong. Though I might sometimes put a better way would be blank. In this case, I would put them in exactly the order I gave them to you. Maybe I'd put the N first, actually. Anyway, it doesn't matter. Okay, so let's do this. This one's annoying because it has 4 elements present in it, right? We've got carbon. So let's start with the carbon. We've got 49.48 grams of carbon. And when we multiply that by 1 mole of carbon being 12.011 grams of carbon, we will get how many moles? 4 point what? 4.1. Give me one more decimal. Great. 4.12 moles of carbon. Which, by the way, that second decimal is overkill for what we're doing, but I like to keep it. All right. Next, if we do hydrogen, we have 5.15 grams of hydrogen. And of course, 1 mole of hydrogen is 1.0079 grams. When we do that, what do I get? Obviously, it's going to be 5, but 5 point what? 5.099. Great. How's that so far? We okay? Am I going too fast? All right. What would I do for oxygen? What would I put here? 49 what? Great. And what do we multiply that by? 1 mole of oxygen, and that's what? 15.9994. If you want 16.00, that's fine. What are we going to get there? Obviously 1 point something. 1.030 grams of oxygen. And the final one remaining is 28. Did I say grams?
Yes.
Whoopsie, sorry about that. And 28.87 grams of nitrogen. And 1 mole of nitrogen is 14 point what? And what do we get when we do that? 2, obviously, 2 point what? 2.06. And obviously, when I look at this quickly, I can pretty much see, because all these decimals are really small, what this is going to round out to. But we should, in fact, divide them all by the smallest one. So if we divide them all by 1.030, it's actually going to clean them up, and they should be even nicer, right? For example, I can see right away that's going to end up being 2.00 moles of nitrogen. That's obviously going to be 1.00 moles of oxygen. What's this end up being? 5.01? 5.00? What's this end up being? 4.95? There we go. Oh, right. Yeah, it's a little cool. And what does this end up being? Just 4.00? Okay. And again, where you rounded might get slightly different. So only one of these even requires any rounding at all. But to be clear, we would have to multiply everything by 20 to get rid of that 0.05. So you either accept that this 4.95 rounds to 5, or that this whole thing is 20 times bigger. What's the safe bet? That it rounds. Which means the empirical formula of this thing would be what? C4, H5, O, N2. Okay. Now, that means that the possible molecular formulae could be C4, H5, ON2, could be C8, H10, O2, N4, could be C12, H15, O3, N6, etc., right? How do we figure out which one it is? Yeah, we can find the molecular weight of the empirical formula. And that would be 4 times 12.011 grams per mole plus 5 times 1.01 grams per mole. And we don't need to go to high sig figs here. There's no use. Plus 16.00 plus 14. Is it 0.01? I always get it wrong. Yeah, so 14.01. And when we do that, oh, and that needs to be multiplied by 2, right? Yeah. Okay, when we do that, what do we get? 97.11? Cool. Okay, now is that the molecular weight they gave us? No. So, we need to find the ratio. So step 1 here would be getting the empirical formula. Step 2 would be the molecular weight of the empirical formula. Step 3 is going to be the mass ratio, right? Just divide them. We're going to say the molar mass of the molecular formula divided by the molar mass of the empirical formula is, what was it, 194 point what? I gave it in the question. Oh, just 194. Great. And we're dividing that by 97.11. And obviously, we're only going to get 3 sig figs here. And it's going to be we're only going to get 3 sig figs, and that's going to be 2.00? 1.99. There we go. Which is obviously what? Yeah. So the actual compound is 2 times the empirical formula, which means that if the empirical formula is C4H5O the molecular formula is what? Well, we're going to multiply all these by 2, and that will give us what? C8, H10, O2, and 4. And if you look up the formula of caffeine, you know what you're going to find? That. How's that feel? Not too bad? 5 stars? Yeah.
So in the beginning of the question, I thought I had it. When you converted like all the things, like say the carbon was like 49.48%, you just converted that straight to grams.
Yeah, so here's the deal.
Yeah.
We know what percentage of this thing is by weight, right? So now, they haven't told you how much weight you have in front of you. Pick a number. You could say, well, if I had 10 grams of this stuff, I could use the percentages to figure out how much I had. If I had 42.5 grams, I could use those percentages to figure out how much stuff I had, right? Well, with percent, what's a really easy number to imagine? 100. So we say, okay, if I had a 100-gram sample in front of me, if I decomposed it, I'd end up with 49.48% of that being carbon. Well, 49.48% of 100 is 49.48. So I'd have 49.48 grams of carbon in front of me. And then 5.15% of the sample would be hydrogen. Well, 5.15% of 100 is 5.15 grams. So if you just assume you have a 100-gram sample, those percentages just become grams and you can go.
Yeah, I messed up really bad.
That's okay.
I immediately went to like, what is it? Making. I don't know how to explain it. I don't explain. I was like.
Can I see it? Would you bring it up?
I was.
Can I take a look?
Running it straight, so like.
Can I see?
The stages.
Um,
Because I went into the calculator and like found
Based on this?
49.48% of 190
that's fine.
grams.
That'll get you that. As long as you do, sure. As long as it's a waste
So
of.
is it just, like,
Here's the deal.
taking
It's
this
a
out?
waste of time. But this will give you the exact same numbers. Now divide all of these by what's that? 1 point? Is that 9?
Yeah, right.
Just divide them all by that. You'll get the exact same answer. Now you've wasted your time. Like I'm not saying that to be rude. Like it would have been quicker for you to just
Convert it to
just work with those numbers. But this will work 100%. Divide them all by that. You're going to get the exact same ratios we got. So finish it your way. Because yeah, you're not wrong. You're working just fine.
Yeah.
So that's fine. Again, you've added a step, but that's fine. Who cares if you add a step? No, Kartik, can I tell you, you're feeling discouraged right now. I would feel the exact opposite. You didn't just follow my rules. You figured it out, and you figured it out. Keep going. You're going to get the right answer. That's great. What's wrong with that? Kartik, what's wrong with zigging when someone zags? That's what the cool kids do. Yeah, you're golden. Stop.
You just haven't been extra steps. You still end up getting it. You still end up getting it.
Yeah.
You good.
In this case, because they just round out, that's fine. But you want to be careful rounding. I consider 0.12 too big to round. When you're doing this kind of thing, rounding a 0.12 down is a big assumption because that's pretty close to 0.25, which would obviously be a quarter, and now you'd have to multiply everything by 4. See what I'm saying? So I would not skip it. I would advise that you want to make sure you're working with the actual ratios, because when we're doing something like this, if I had to round to 0.12, I would say, I don't like that. I'm going to redo if I was really in the lab, I'd say, we got to run this again. That's too big to round. Does that make sense? Because really 0.125 is 1/8. So maybe I need to multiply all these by 8 instead of rounding. See what I'm saying? You can't just be like, I'm going to round it and go, because you might end up with a wonky formula. In this case, you would have known because the ratio of the empirical formula and the molecular formula ends up being perfect, so you can trust it. But if it didn't work out, then you'd have to go back to the drawing board. So, like, I'm of two minds here, because the truth is, yeah, you're fine, but I'm not comfortable with that level of rounding when working on something like this. Even though in this case it works.
What would you say?
Because just because something works doesn't mean it was a good habit, you know?
What do you think is a good like number to round for? Like
I would say that you would want to,
0.05?
I would say that if you are more than 0.5 off in the real world, you'd want to redo these. You'd want to at least do it 5 times and make sure you were getting consistent results.
Okay.
Which is why I'm not going to give you, I won't give you questions that require big rounds. I went and saw this band once, and it was like jazzcore math rock, all played on a ukulele, then with like deep synths and like electric bass behind it, and it was so good.
I didn't know that existed, but I'm like really curious now. That sounds really cool.
I got a lot of this stuff. Like,
That stuff is good. I like her. Keep that.
a bell! Box. I don't care if there's a minute left. Box. Oh my goodness, indeed. Box. I don't care. Put on the lectern in blatant defiance. Go sit down. Go sit down. What are you, a grade 9? Is that what you are? You're grade 9? Defying my pretty much. No, you're a grade 10. You're a grade 10. And you're a leader of grade 10s, because here you are in a grade 11 class. So I hold you to a higher standard. I didn't see Alex. I saw you blatantly defying my rules. Love that kid. Big fan.